How might Newton interpret gravity? It was sufficient to permit us to fly from the Earth to the Moon, at any point winding up lost in the ticking hands of time, contemplating whether how we might interpret it is only the tip of the transient iceberg. On its head, his disclosure isn't a hypothesis. A key could open the ways to the secrets of the universe, uncovering a universe more multifaceted and motivating than we at any point thought about envisioning. How does Brian Cox's new hypothesis challenge our conventional understanding of time? And what are the possible ramifications for our impression of reality? Join us on a captivating investigation through the annals of time itself as we dive into Brian Cox's recently uncovered historic hypothesis on the idea of time in the immense universe around us. Secrets are ready to be uncovered, and a portion of these secrets include baffling things. Finally, gravity, which are fundamental pieces of our reality. Imagine an existence where time acts unusually, can either dial back or accelerate. Additionally, the force that keeps us on the ground probably won't be what it appears to be. This is the domain of Albert Einstein's theories of relativity, where how we might interpret time and gravity veers off in an unexpected direction. Albert Einstein, a notable name, furnished us with a better way of looking at the universe through his hypotheses of relativity. His work established the groundwork for understanding how time acts in various circumstances, particularly while going at very high velocities. Everything started in the mid-20th century when Einstein proposed two momentous speculations: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, changed how we might interpret existence. In simple terms, it tells us that the laws of physics remain the same for all observers who aren't accelerating, no matter what their motion. This hypothesis presents the possibility of relativistic effects, including the popular idea that time can stretch or slow down under certain circumstances. One interesting psychological study used to explain time dilation is the light clock. Imagine being inside a spaceship moving incredibly fast, nearly at the speed of light. Inside the spaceship, there's a light beam bouncing between two mirrors, perpendicular to the direction of movement. According to the laws of physics, the speed of light is constant for all observers, so the light beam should seem to travel along a longer diagonal path. The time it takes for the light beam to travel this way should be the same for both the observer inside the spaceship and the one outside. However, since the path is longer for the external observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer moving relative to the stationary observer in this situation. Time acts differently depending on your movement. Understanding how things change when they move quickly, known as relativistic effects, isn't just a theoretical concept. Scientists use huge machines like particle accelerators such as the Large Hadron Collider to make particles move fast, nearly as fast as light. When things move this fast, we need to think of time in a very special way to make precise predictions and calculations. Albert Einstein developed the special theory of relativity in 1905, and it changed how we see the universe, especially regarding time and motion. This hypothesis challenges what we would normally think. It says that the laws of physics are the same for everyone, whether or not they're moving. This is different from our everyday experience, where we might feel that if something is already moving and we add more speed, it gets faster. But Einstein's theory says there's a maximum speed that nothing can exceed, and that is the speed of light. From this perspective, events that seem to occur simultaneously for us might not appear that way for people moving nearly as fast as light. Another idea that comes from this unique viewpoint is length contraction. This means that if something is moving, it looks shorter in the direction of motion when viewed from a stationary spot. Then there's the famous equation, E equals mc squared, which shows how energy and mass can transform into one another. This is crucial for understanding how tiny particles behave when they're zipping around super fast, and also for things like what happens when atoms split in nuclear reactions. In practice, special relativity isn't just a fancy theory, it's something we use in everyday technology like GPS. When GPS satellites send signals to your device, they are moving, and because of this movement, time acts a bit differently for them. If we didn't account for this time dilation effect in our GPS calculations, your navigation would be inaccurate. So, special relativity teaches us that time isn't the same for everything and everywhere. It depends on how things are moving. This idea challenges our perception of reality. It's like saying our usual understanding of the universe is a little off. According to the special theory of relativity, time isn't fixed. It's affected by movement. Some basic ideas like the constant speed of light and how energy and mass are connected have been proven by numerous experiments. But there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory digs deep into the relationship between gravity and how the universe is structured. It overturns the old idea that gravity is just a force that pulls things from a distance. Instead, it tells us that gravity happens because spacetime is bent or curved. It's like saying gravity is not a mysterious force. It's simply how things naturally move in the universe. According to Brian's understanding, general relativity means thinking about the universe as a four-dimensional entity, combining 3 dimensions of space and 1 of time. In this framework, big objects like stars, planets, and even us influence how spacetime is shaped around them. This shaping is what we experience as gravity. Imagine spacetime like a big stretchy blanket. When something heavy like Earth is placed on it, it creates a dent in the blanket. If you place something smaller like a ball near Earth, it will move toward this dent. This is similar to how objects behave due to gravity. Not a strange force, but a response to the bending of spacetime. General relativity provides a solid explanation for how things move in our solar system, such as planets orbiting the Sun. It can accurately predict the paths these planets take, including how Earth follows an oval-shaped orbit around the Sun. According to Brian, this is different from the old notion of gravity as just objects attracting each other, which struggled to explain how planets move as they do. The novel idea is that space-time is bent like a flexible fabric, which fits better with what we observe. A pivotal moment that confirmed the accuracy of general relativity occurred during a solar eclipse in 1919. Sir Arthur Eddington led a team to observe how light from distant stars bent as it passed near the Sun. According to the theory, the Sun's mass would cause starlight to bend slightly during the eclipse, and the observations matched Einstein's predictions, validating the theory. Just as motion can change how we experience time according to special relativity, gravity also affects time. In places where gravity is strong, time moves more slowly compared to areas with weaker gravity. So, if you were standing near a massive object like a black hole, your clock would tick more slowly than one placed far from this massive body. General relativity introduces black holes, which are regions where gravity is so strong that nothing, not even light, can escape from them. The boundary surrounding a black hole is known as the event horizon, and it's like a final threshold. Once something crosses this boundary, it gets sucked into the black hole with no chance of returning. Einstein's theory of general relativity has profound implications for how the universe is structured. Initially, he added something called the cosmological constant to his equations because he thought the universe was static. However, when we discovered that the universe is expanding, he called it a major mistake. The idea of an expanding universe revolutionized our understanding of the cosmos, suggesting that space itself is stretching over time. This discovery led to the understanding that the universe was not static but dynamic, constantly changing and evolving. Over time, scientists began to recognize the significance of Einstein's general theory of relativity in explaining cosmic phenomena, particularly the behavior of galaxies, the formation of black holes, and the expansion of the universe. In modern cosmology, general relativity continues to play a key role in our understanding of how the universe works on a grand scale. It provides the framework for understanding the behavior of massive objects, such as stars, galaxies, and black holes, and how they interact with spacetime. In fact, one of the most fascinating aspects of modern science is the study of black holes, which were predicted by general relativity and have become a central focus of astrophysics. The discovery of the cosmic microwave background radiation, the expansion of the universe, and the observation of gravitational waves. All of these phenomena have deep connections to Einstein's theory. Scientists are still uncovering new aspects of general relativity, using it to probe some of the most mysterious and extreme environments in the universe. For example, when studying the collision of black holes, or the behavior of light around massive objects like neutron stars, general relativity continues to provide invaluable insights. Furthermore, general relativity has led to significant technological advancements. It has helped shape GPS systems, as we discussed earlier, and has influenced the development of technologies related to space travel and satellite communications. Its impact extends far beyond theoretical physics, influencing practical applications in ways we may not always recognize. As scientists continue to explore the vast reaches of the cosmos, Einstein's theory remains a cornerstone of modern physics. However, challenges remain in fully reconciling general relativity with quantum mechanics, which governs the microscopic world. This search for a unified theory of everything is one of the most exciting frontiers in science today. In conclusion, Einstein's theories of relativity have had a profound impact on our understanding of the universe. From time dilation to the bending of spacetime by massive objects, his insights have reshaped the way we think about gravity, time, and the nature of the cosmos. While his work continues to influence the scientific community, new discoveries are pushing the boundaries of what we know, reminding us that there is still much to learn about the universe and the fundamental forces that govern it. The universe, in view of general relativity, is a critical piece of the theory of prehistoric cosmic detonation, which makes sense of how the universe started. One more significant idea from general relativity is gravitational waves. These are swells in the texture of existence, brought about by exceptionally gigantic objects moving quickly, like when black holes or neutron stars converge. In 2015, researchers at the Laser Interferometer Gravitational Wave Observatory directly identified gravitational waves, giving verification to one more part of Einstein's hypothesis. Over time, researchers have conducted various tests to check whether general relativity is valid, and each time it has shown to be right, whether by seeing how planets move, the bending of starlight, or the detection of gravitational waves. While saying gravity is completely false may be astonishing, particularly since we all experience gravity consistently, in the realm of physics, it's not unexpected to discuss and investigate various ideas. Researchers like Brian often question established theories, and in the domain of gravity, some test the regular way we think about this central force. One idea that challenges conventional gravity is called modified Newtonian dynamics, MOND, which suggests that gravity acts differently at slow speeds, especially in galaxies, without the need for dark matter. Instead of adding invisible matter, MOND suggests that gravity strengthens at low velocities. The gravity debate also includes the mysterious concepts of dark matter and dark energy, introduced to explain certain anomalies in space. Critics argue that these aren't necessary and that alternative ideas can explain what we observe. Some researchers who disagree with Einstein's theory of gravity explore other possibilities, such as theories involving unknown particles or forces that could change or improve how we understand gravity. It's important to stress that in science, novel ideas are not dismissed. Rather, they are thoroughly tested to check whether they make sense. For example, Einstein's idea of spacetime, where time travel may be restricted by the speed of light, has been creatively considered alongside ideas like wormholes and shortcuts. Stephen Hawking's no-boundary conjecture suggests that traveling back into the past seems unlikely from a physics perspective. Ongoing studies and observations aim to determine whether these new hypotheses can explain phenomena in a way consistent with what we already know. While different ideas have been explored, none have convincingly replaced the fundamental principles of gravity. Questioning and testing established ideas are vital parts of how science advances, leading to further exploration and a deeper understanding of the universe. In the realm of gravity theories, general relativity remains the most significant and successful one. Despite challenges and alternative ideas, it consistently performs well in tests and explains various phenomena, such as how planets move and how light curves around massive objects. General relativity remains solid because it is simple and encompasses a wide range of phenomena. As previously discussed, Einstein's theory of relativity proposes that time can act differently based on what you're moving through. Now, let's explore how this idea affects real-life situations, particularly in space travel. Space travel is exciting yet challenging, since space is vast, and according to Einstein's theory, the speed of light is the fastest anything can go. This makes traveling between stars a significant challenge, even with advanced technology, because of the long time it takes to reach the nearest stars. Consider the famous twin paradox. To understand what happens with time when you travel in space, picture this. One twin stays on Earth, while the other twin embarks on a fast journey to a distant star. When the space-traveling twin returns, they find that less time has passed for them than for their twin on Earth. This means they have effectively traveled into the future. Time is crucial for space explorers because the longer the journey, the more time slows down. If astronauts were to visit nearby stars, where time slows down significantly, they could age more slowly than people on Earth. While this may seem like science fiction, it's a real effect from the theory of relativity. Imagine if humans send a crew to a star system not too far away. Due to the immense distance, the trip could take many years, even if they travel quickly. For the astronauts on the spaceship, time would feel more limited because of the time dilation effect, but on Earth, much more time would have passed. Time dilation affects not just living beings but also technology. Computers and other technical devices on spacecraft would need to account for time dilation for accuracy and proper functioning. Space travel at high speeds presents physical challenges, such as prolonged isolation and exposure to cosmic radiation, as well as the psychological effects of being away from Earth for extended periods. In our daily lives, we can notice the effects of time dilation in the Global Positioning System, GPS. GPS relies on the precise timing of signals from moving satellites. Since these satellites experience time dilation, it's important to account for these effects to ensure accurate GPS calculations. Failing to do so would significantly affect the accuracy of navigation systems. Now let's explore why time moves in one direction. Time governs our lives in the universe, moving from the past to the present and into the future. This one-way journey of time is key to our reality. But why does time have this one-way nature? To understand, we look at entropy, a concept that measures disorder or irregularity in a system. Entropy, connected to the arrow of time, tends to increase over time, making time flow in one direction. The second law of thermodynamics expresses this relationship, stating that in any isolated system, total entropy will either increase or, at best, remain constant. In simple terms, entropy naturally tends to increase and doesn't decrease on its own. Seeing how things become more disordered around us helps us understand the one-way progression of time. Imagine a deck of cards, neatly ordered. If we shuffle them, they become messy and random. This change from order to disorder illustrates how time moves in one direction, as seen in everyday phenomena like ice melting or a stirred cup of coffee becoming turbulent.